Hi, welcome to Measure Theory 22nd session on Lebesgue Integral session number 5. Today we are going to talk about another important convergence theorem of Lebesgue Integral, namely Fatou's lemma. Okay, I will try to motivate what it means. Suppose you are given a sequence of real numbers an, the sequence may not converge. The limit an may not exist. But we have seen that it's useful to talk about lim in and lim sup of the sequence an. Okay, so even with that also we can prove a lot of results we have seen. So Fatou's lemma addresses such a problem. I have sequence Fn of non-negative measurable functions. Fn may not converge at all point-wise. Okay, but I want to compare the integral of the lim in and the lim in of the integrals. Okay, why I can't do with the supreme lim sup? Okay, again there is a problem. All boil down to only one thing. Okay, if En increases to E, measure of En increases to measure of E, but if En decreases to E, measure of En may not decrease to measure of E. Unless I put extra condition, at least one of the En's, usually E1, measure of E1 is less than infinity, it's finite. Okay, you had already seen in monotone convergence theorem also. This perpetuates everywhere, right? So that result, okay, let us state the result. Yeah, so Fatou's lemma. So what I have yes, B, mu, a measure space, right? And Fn, a sequence of non-negative measurable function. For all n in n, right? Then I can talk about lim inf of Fn. So recall what is the lim inf of Fn? Okay, it may be useful. Lim inf of Fn at x for x in x is nothing other than lim inf of this sequence of numbers. Okay, so lim inf of Fn, think of it as a function whose value at x is this. We had already done that when we dealt with measurable functions. Okay, this one. So I want to talk about two things. One is lim inf of Fn, and then lim inf of integral Fn. Is there any relation? Are they equal? Less than or equal to, greater than or equal to? Okay. I have a mnemonic for this. The result is actually, if I remember right, this must be this. But I have an example which also is a counter example in the sense that this inequality, this strict inequality can happen. Okay, so that example is the one which tells me whether this should be this way or this way. Okay, which one? Okay, I'm worried. All right, the example is, look at this we had already seen this one, right? Then Fn actually converges to 0, therefore lim inf of Fn is a limit of Fn which is 0, but therefore integral of lim n of Fn is 0, but integral of Fn is always infinity because it's the character indicator function of the infinite interval, right? Therefore lim n of Fn, integral Fn is also infinity. So therefore the correct one is this. And this also, this example gives a thing, a strict inequality hold. Okay, this example also explains. Okay, so pause, review, proceed. proof is an easy application of monotone convergence theorem. So for monotone convergence theorem, what do we need? We need an increasing sequence of measurable functions. Let us say they increase to g, then it says integral gn. The limit of this is limit of integral g, which is same as saying integral gn increases to integral g. Integral g. This is our MCT. So I have to think of an increasing sequence. You are given me an fn. Okay. So the obvious thing is to say this. Right? So if you had understood limbs in limb soup, the obvious way to generate is this. Define Gn to be the infimum of Fk, k greater than equal to n. Okay, what does that mean? This means Gn is a function whose value at x is, look at the infimum of this set, Fk of x for k greater than equal to n. This is infimum of the set Fk of x, Fk plus 1 of x, and so on. Right? Therefore, Gn plus 1 of x, you can see, okay, will be greater than equal to Gn of x because it's the infimum of Fk plus 1 also. Therefore, we know that Gn of x is less than equal to Gn plus 1 of x. And we also know from our sequence of measurable functions section, each Gn is measurable. Measurable. And Gn increases. Where does it increase to? It increases to limit of Fn. Okay, call it F if you want. Right? This is the definition of limit. Right? Notice that this is increasing, therefore Gn of x, okay, has to converge to some limit of x. Remember, this we are all in non-negative things, therefore it will, when I say it converges, the possible value infinite is a possible value. Okay, but this by definition is this. Okay, right. So we got it. Is this clear? Right. Next thing we want to observe, what is the relation between Gn and Fn? Notice that Gn is infimum of Fn plus 1 onwards, therefore Gn is always less than equal to Fn for all n. Right? Right. The next result we need about this, if an is a sequence of numbers, and suppose a and bn are sequence of numbers, if an is less than equal to bn, then limit of an is less than equal to limit of bn. Okay, this is very easy, right? Because an is less than equal to bn, therefore you can see the infimum of a k greater than equal to n will be less than equal to infimum of bk k greater than equal to n. Alright, if alpha k, let us say sk is the infimum, then sk is less than equal to ak for all k greater than equal to n, but ak is less than equal to bk for all k, therefore sk is, okay, this Sn will be less than equal to Bk for all k greater than equal to n. And infimum is the greatest lower bound, Sn is a lower bound, therefore Sn is less than equal to this infimum. Okay, you see that? This is the kind of thing you have to keep repeating so that you become very confident. Okay, otherwise, you should not be, intimidated the moment you see limb soup. Anyway, right? Therefore, integral of Gn by monotonicity, remember we are all in non-negative measurable functions. Therefore, monotonicity is valid for integrals. Integral Fn, right? And now I can use this result. Therefore, okay, lim n of integral Gn is less than equal to lim of integral Fn. Is that okay? Right? Now we are ready for everything. So keep this as 1. Let us start with, what is integral of f? Integral of f is limit integral of Gn, because Gn increases to f. These are all non-negative functions. Okay, therefore monotone convergence theorem says integral of it. But remember again, if the limit of numbers exists is same as lim inf of integral g, right? But this from 1, this is less than or equal to lim inf of integral fn. But what is this? This is by definition integral of lim inf of fn. So lim inf of fn is less than or equal to lim inf of integral fn. So we proved the result. Okay, pause, review, proceed. So only concentrate on these two things. Okay. Note that the proof is looks extremely simple, but it's not all that easy. Okay, there are subtle arguments because we keep on changing various things. Whenever say sequence converges, the limit is same as lim inf or lim sup. So we are trying to use that. Okay, Gn increases to lim inf of Fn. Therefore, by monotone convergence theorem, integral Gn increases to integral of F, where integral of F is lim inf. Okay, but then what we do is then integral Gn is the less than equal to integral Fn. Therefore, lim inf of integral F Gn is less than equal to lim inf of integral Fn. So keeping all those things together, we got it. Okay. All right. Please go through that. Stop the video and go through the proof in your mind again or with a pen and paper. Yeah, there is one more thing. See, Fatou's lemma is an important tool. Okay, as I said, there are three convergence results, three results which involve sequences and integral in Lebesgue integral, in the theory of Lebesgue integration. Two of them we had already seen. One is monotone convergence theorem, and it talks about only increasing sequence of non-negative measurable functions. Okay, remember it's non-negative again. And similarly, Fatou's lemma, that again talks about only non-negative measurable functions, but then it doesn't say equality. It says integral of the lim inf of the functions is less than or equal to lim inf of the integrals. Okay, this is what it says. Okay, and many times this Fatou's lemma is kind of underappreciated. It's not appreciated as much as it deserves. For there are two reasons as far as I can see from my experience. The first thing is many students are very uncomfortable with the lim inf concept, number one. Okay, there is some kind of psychological stigma. The second thing is you expect, see, all the analysis thing essentially says, okay, I can interchange the limit with something else, some operation, integration, and limit can be interchanged. Here I am not interchanging lim inf of integral and lim inf. Okay, there is an inequality. So they think it's of not much use. Okay, but you will see it's an important tool. We are going to use it many times in our course. Okay, so please learn to appreciate that thing. We are going to give only typical application. That is the way it is used. Fatou's lemma is though, even though it talks about less than or equal to, it can be useful to prove equality. Yeah, we are going to see that. So an application, only one application for the time being. Let me see. I have screen shared. Yes, it's doing right. Okay. So again, let us assume X be mu measure space. The Fn's are non-negative functions, non-negative measurable function, and F x to 0 infinity is measurable. Assume two things. Okay, Fn is less than or equal to F for Rn, and okay, and Fn converge to F pointwise. Right? Then you want to say limit integral Fn is integral limit Fn, which of course is integral F. Yeah? Do you see this result? Yeah. So I am not saying fn increases to f. What all I know is this. And a word of caution, if you had already gone through Lebesgue integral or measure theory, you may think fn's are dominated by f and fn converges to f. Therefore, this should follow from dominated convergence theorem. Okay, if you have not gone through, please ignore what I am saying. I mean, whatever I am going to say within the pink box, you can ignore. Okay, that's not true because integral f may be infinite. Therefore, this may not be integrable function. For dct, the dominating function f should be integrable. Again, the word integrable I have not yet defined. Okay, those who are the first timers should ignore whatever I talked about. Okay, because there are always people who think, okay, they already understood, so it is very easy. Okay, there is a subtlety. Subtlety is integral f may be infinite. Okay, right. So let's come back to the proof. So I want to use Fatou's lemma now. So what does Fatou's lemma says? Fatou's lemma says since fn, okay, integral of lim inf of fn is less than or equal to lim inf of integral fn. Is that okay? Right. Yeah. But what is this? Remember, fn converges to f, right? Therefore, lim of fn is same as lim inf of fn, right? Therefore, this fellow is nothing other than integral f. Is that clear? Right? Okay. Now the next thing is, notice that whenever a sequence I have an, lim inf of an is less than or equal to lim sup of an. Therefore, this is less than or equal to lim sup of integral fn. Right? Now notice that each fn is less than or equal to f. Right? Therefore, lim sup of fn is less than or equal to lim sup of f. Right? Therefore, by monotonicity, integral fn, let me just go slow. Fn is less than or equal to f, therefore integral fn is less than or equal to integral f. Right? Now look at these numbers. Okay, these are all bounded above by integral of f. Therefore, lim sup of these numbers is less than or equal to this. Therefore, this is less than or equal to integral of f. Okay. For again, let me take a digression, because I am always, maybe you should, in the comments, you should say, sir, this is enough. We are comfortable with lim sup in pip. Okay. Please go ahead. Okay. Otherwise, I'll keep repeating. See, if an is a sequence, okay, and suppose bn is another sequence, again the same thing, an is less than or equal to bn for all n, then lim sup of an is less than or equal to lim sup of bn. And in this case, our bn may be a constant b. That's all we have done. Okay, this is very easy because look at supremum of a k greater than or equal to n. This will be less than or equal to supremum of bk greater than or equal to n. Right? Therefore, the limit of this will be less than or equal to limit of this. But that is lim sup. Okay, that's a thing. Okay, pause, review, proceed. Now come back. Therefore, what is thing I have shown? I have shown integral f is less than or equal to lim inf of this integral of the lim in. Okay, that is less than or equal to lim inf of the integrals, but that's less than or equal to lim sup of the integral, and that's less than or equal to integral f. That means equality holds everywhere. And second, notice that when I gave integral f and this sequence of numbers in 0 infinity, okay, I do not know if it converge at all. Converge here. Okay, maybe it is equal to infinity, but I will simply say converge. That is whether the limit exists. That's not clear. Right? But But what I know is lim in, I can talk about lim in for interlepen, lim super interlepen. Now we are saying equality holds everywhere. That means these two are the same. So as a corollary, what you have done is limit of interlepen exists and it is equal to interlepen. Okay. So the correct way of formulating the theorem is I do not know whether it exists. Therefore, then limit interlepen exists and we have limit interval equal to interlepen. Okay. Pause. Review. Proceed. Yes. Okay. You can see that analysis one has to go through a little carefully. Alright. Not simply manipulating symbols. For example, I simply wrote limit of interlepen. But the point is why the limit exists. That's all. So it's part of the conclusion. The sequence, namely sequence of interlepens, that limit exists and the limit equal to interval of f. That is the theorem. Yeah. Can you think of its use anywhere? Just think about what is the assumption. F1s are non-negative measurable, F1 less than or equal to F. Right? And F1 converges to F. Therefore, interval F1 converges to interval F. Can you think of an application of this application? Fatou's lemma, we had application and an application of the application. Second order. Monotone convergence theorem. Why? If F1s are non-negative measurable, they increase to F. That means F1s are less than or equal to F. Therefore, interval F1 must converge to interval F by this application. You understand that? Therefore, I can deduce monotone convergence theorem from Fatou's lemma. Right? You understand this? So let us go back. So, application of Fatou's lemma implies MCT. That means Fatou's lemma implies LCT. Okay? Because the F1s increase to F, okay, then F1s are less than or equal to F. They are all measurable. Therefore, interval F1, okay, limit of interval F1 equal to interval F. So, we proved it. Okay? Okay. So, whatever we wanted to talk about, integral of non-negative measurable functions are done. There are two important results. One is monotone convergence theorem. The other one is Fatou's lemma. Both deal with non-negative measurable functions. So far, we have not defined interval of a measurable function. Okay, now we want to define that. Okay, let me just motivate, then we'll go and define it. See, suppose I start with the measure space x b mu, and f is a measurable function from x to r, or if you want extended, I don't care. Okay, then how do I define? The standard trick in mathematics is reduce the problem to something what we already know. Yeah. So what do we know? We know how to talk about interval of a non-negative measurable function. We had already seen, given any measure function f, I can write it as f plus minus f minus. F plus is also non-negative, f minus is also non-negative. We had also seen if f is measurable, both f plus and f minus are measurable non-negative functions. Therefore, I can talk about interval of f plus and interval of f minus. And in my mind, I always want my integral to be linear. Therefore, what is a very natural way of defining interval f? Obvious, right? F equal to f plus minus f minus. Therefore, interval f must be equal to interval f plus minus interval f minus. You understand? But do you see a problem there? The problem is interval f plus may be infinity. Interval f minus may also be infinity. Then I will be left with infinity minus infinity. So, we have to exclude that case. Is that clear? So, let us start. So, this is the next section, integral of measurable functions. So let x to R or Re be measurable, right? Then write f as f plus minus f minus, right? Then we want to define integral of d mu over x to be integral of f plus d mu, sorry, d mu over x minus integral of f minus d mu over x. So provided, this is the important thing, one of these two is finite. Either this is finite or this is finite. Then I don't care. For example, this is finite. Let's say alpha and beta. Okay. If alpha is finite, then it's okay. Alpha minus beta makes sense. Or if beta is finite, then again alpha minus beta makes sense. Alright. If beta is infinity, this will be minus infinity. If here beta is infinity, alpha is finite, this will be, as if alpha is infinity, beta is less than infinity, this will be plus infinity. You understand that? So we will define, we do not define integral of any measurable function, only, okay, we look at integral of f plus and integral of f minus, one of them must be finite. Then we can define integral of f. Okay, please understand this. Okay. Now, there are few observations I have to look at. Notice that we know that mod f is f plus f minus, right? This we already know. Now notice that these are all non-negative measurable functions. And therefore, we can integrate, and integral is additive or non-negative measurable function. Therefore, modulus of integral will be integral of f plus integral of f minus. But both are finite, right? Therefore, this is also finite. You understand this? Yeah? Okay. So, now we are going to make a definition. Let f x be mu to Re be measurable. We say f is integrable or mu integrable. Okay. On x, f integral f d mu is finite. Okay. So what does that mean? This happens if only if integral f plus d mu is finite and integral f minus d mu is finite. Right? Therefore, it's integrable if only if these two integrals are finite. Right? But then this means if f is integrable, as usual again disturbances. So f is integrable implies mod f is integrable. Why? Because mod f is f plus f minus, and just now we saw if these two integrals of these fellows are finite, then the integral of this fellow is finite, right? Converse is also true. Okay, we want to claim this one. That is very clear because notice that f plus is less than equal to mod f and f minus is also less than equal to mod f, right? Therefore, yeah, is it clear? Both are finite. Therefore, integral of f plus is finite and integral of f minus is also finite. That means f is integrable. So what have we shown? So this is a very important observation. Okay. F is integrable if and only if mod f is integrable. This is one of the most important observations about Lebesgue integral. In fact, I consider this is the strength of Lebesgue integral as well as the weakness of Lebesgue integral. Why it's weakness, we will see it, okay, as we go along. What is the strength? Why? You will try to understand. Okay, we will try to look at a very special case, try to understand why it is something very stringent condition, right? For two reasons. First, let us contrast with Riemann integral. Then we will also look at a very specific particular example of measure space and try to see what it means to say integrability. Yeah. So this is the way you will really understand Lebesgue integral. So let us go ahead. The first thing is, let us look at Riemann integral. Okay. So let us stick to 0, 1. So I modify the Dirichlet function as follows. Okay. So f of x equal to 1 if x belong to Q intersection with 0, 1 and equal to x is in 0, 1 and equal to minus 1 if x is not in Q. Remember, it's always in 0, 1. Right? And then this is a modified Dirichlet function. This is not integrable. It's not Riemann integral. But what is mod f? Mod f is constant 1 is Riemann integral. Okay, this shows the contrast. Here in Lebesgue integral, we saw f is integrable if only mod f is integrable. Whereas in Riemann, if f is integrable, mod f is integrable, but the converse is not true. Mod f may be integrable, but f is not integrable. That's one thing. Second, let us look at the special cases. So let x be equal to n and b equal to power set of n and mu equal to counting measure. Okay. And so let us look at a function f from x to r. Okay. Right. So this sequence we use, then we think of this as a sequence an. Right. Now what is f plus? F plus is whenever f plus at n is an if n is greater than or equal to 0. An is greater than or equal to 0, otherwise 0. Right. And similarly f minus. F minus of n is minus an if an is less than 0, otherwise 0. Right. Maximum of both. This is what we did. Right. So in particular, let me look at the alternating thing, minus 1 to the power n plus 1 by n. Okay. Now, what is f plus? So I have 1 and minus half and 1 by 3 minus 1 by 4, 1 by 5 minus 1 by 6 and 1 by 2n minus 1 and minus 1 by 2n and so on. Right. Therefore, my f plus is going to be this. And this is going to be my f minus. Right. Now, what is f plus and f minus? Okay. And we had seen f plus is going to be 1, 0, 1 by 3, 0, 1 by 5, etc. so on. And similarly f minus. And we had already seen what is the integral of f plus. Integral of f plus with respect to the counting measure over n is nothing other than summation of f plus of n, which is nothing other than essentially 1 by 2n minus 1 n equal to 1 to infinity. This is divergent. And similarly f minus d mu is summation 1 by n, which is divergent. 1 by 2n. Right? But remember, if I look at what I think, if I think integral is in some way generalizing the sum, then let us look at this. This is nothing other than minus 1 to the power n plus 1 by n equal to 1 to infinity, this is conversion. Okay, this is alternating series is conversion, right? And we know it's important to look at such a series. Okay, but this series is not absolutely conversion, because that is summation 1 by n. Okay, so let us try to understand what this example says. The first thing is, if I look at f of n equal to minus 1 to the power n plus 1 by n, okay, then this, the the integral of mod f is summation mod fn, which is summation 1 by n, that is divergent. But if I simply look at summation 1 by minus 1 to the power n plus 1 by n, that is the standard convergent alternating series. Alright. So therefore, what does it say? It says that, okay, something may be convergent, but mod f may not be convergent. That's not important. But the important thing is the following. So when I want to talk about convergence of a series, okay, we know that absolute convergence implies convergence, but the converse is not true, right? And if I think of integral as a generalization of sum, okay, I would think that summation fn should also make sense. But Lebesgue integral says no, it can't. Because you can define summation fn only if summation f plus n and plus summation f minus n makes sense. They are finite, which is not the case. You follow, right? Therefore, the strength is the integral exists if only mod f is integrable. That is strength, because it's a very stringent condition. But it's a weakness because there are reasons why I want to look at like alternating series. You know that it is the sum of the series log of 1 plus x equal to 1, that is log 2. Okay, it's one of the beautiful results following from Weber's limit theorem. Okay, so that's a beautiful result. So we have to deal with such alternating series. Later also we will see, okay, there are some integrals, improper Riemann integrals which exist, which are very important in signal processing, etc. But the Lebesgue integral of such function do not exist. Okay, so if any of your teachers or your seniors give the impression as though Lebesgue integral is a very good, you don't have to worry about Riemann integral, don't believe that. Okay, Riemann integral is also important. Okay, because Lebesgue integral is much more stringent. Stringent in the sense it says f is integrable if only mod f is integrable. That's a very strong condition. Okay, right? Sometimes some kind of flexibility is also important. Sometimes, right? But it has its own merit. We are going to see that. Okay, these are the things which are never explained. They immediately they want to prove theorem, but you should appreciate, okay, this result. And even if you don't understand 100% of what I'm saying, it's okay. Don't bother. Even this kind of understanding will help you get some foothold about Lebesgue integral. Okay, let's go ahead. Now we want to prove algebra of integrable functions. So let us introduce a notation and we'll start proving that. So the next thing is, let L plus of x be mu be the set of integrable functions. Of course, mu integral function on x, etc. These are all, okay, tacitly assumed. And I will simply say L plus so that I don't keep writing this. Okay. So what are the things you want to do? The first thing you want to do is, suppose f and g are here. I want to know f plus g is in L plus. This is the first condition, whether it goes under addition. Okay. Therefore, the usual thing is, whenever we have function space sequence, convergent sequences, then they form vector space. The convergent series, they form vector space. And the set of continuous function, some set, they form vector space, differential function. So these are the, we are always obsessed with this kind of extra algebraic structure. So we want to look at this. Okay. Let me see whether I'm sharing the screen. Yes. Okay. Now let's call h equal to f plus g. Okay. I want to talk about integral of h equal to integral f plus integral g. This is what I want to prove. Right? But how did I define integral g? H. That's only by writing h equal to h plus minus h minus. Right? Therefore, integral h by definition was integral of h plus minus integral of h minus. Right? Now, for f also we did the same thing. F equal to f plus minus f minus and g equal to g plus minus g minus. Notice that h plus is not f plus plus g plus. True. I write my inverse, but it's g minus. Right? Because my, let us say, h of x, my f of x may be 10, my g of x minus 1, let us say minus 2, then f plus g of x will be 8. You understand that? Yeah. Whereas here f plus will be 10, f plus at x will be 10, and g plus at x will be 0. We are not having this. Okay? So this is not true. So we have to do a little more carefully. Okay? Before doing, there is one thing which there is a very important observation. Which, okay? Suppose f from x to re is measurable and g from x to 0 infinity measurable, integrable. Okay? Notice that this means for non-negative function g equal to g plus and g minus is 0. Right? Therefore, this is, when I say integrable, it simply means g plus is finite. Right? So assume f mod f is less than or equal to g. Then we want to claim f is integrable. Do you understand this? So this gives a criterion of when a measurable function is integrable. I only have to look for an integrable non-negative function which dominates mod f. We say g dominates mod f. Okay. Then I want to prove f is integrable. Okay. But remember, f is integrable is same as saying mod f is integrable. Right? But that's very clear because mod f is measurable, therefore mod f is measurable, and mod f is less than or equal to mod g, therefore integral of mod f is less than or equal to integral of g. This is finite. Right? Therefore this is also finite. That means mod f is integrable. Okay? Or if you want separately, you can do that. F plus is less than or equal to mod f, that's less than or equal to g, therefore mod f plus is less than or equal to integral of mod f, which is less than or equal to or integral g, etc. Therefore this is finite. Similarly, integral f minus is finite. Do you understand this? This observation is a extremely easy, simple observation, but very useful. Okay, let us use that. So I have f and g. Okay, they are in L plus integrable. Then I want to say f plus g is integrable first. Therefore, integral f, that is h. Therefore, integral h makes sense. Okay. Next, I want to say the integral h is nothing other than integral f plus integral g. Okay, this is what we want to prove. Okay. You see that I am thinking aloud and explaining once again what I wrote simply as a theorem. Okay. Why this is integrable? That is very easy. Because let us look at mod h. Mod h is less than or equal to mod f plus mod g. Right? Now mod f, integral mod f is finite because f is integral. Similarly, mod g is finite. Therefore, and yeah. So you call this as function phi, then phi is non-negative measurable. And integral of phi is mod f plus mod g. That's finite. Because this is finite, right? Therefore, mod h, integral of mod h is finite. This is monotonicity, right? Mod h is less than or equal to phi. right? Therefore, by monotonicity, mod h is less than equal to integral of mod h is less than equal to integral of phi, but integral of phi is sum of these integrals, which is finite. Therefore, this is finite. Therefore, h is integrable. Okay, pause, review, proceed. Now, as I said earlier, h equal to h plus minus h minus, integral of h is equal to integral of h plus minus integral of h minus. The first observation, since I said h is integrable, notice that these are all finite. Right? Okay. And again, as I said, there is no relation between h plus, f plus and g plus. Okay? You cannot connect them. No relation. Okay? Therefore, this is what I mentioned here. Yeah. Okay? This is what I mentioned here. So there is no relation. So the way we want to do that is, let's look at integral of h. Integral of h by definition is integral of h minus h plus integral h minus. But integral of h is integral of f plus g. Right? Now what is integral of f? Integral of f is integral of f plus minus integral of f minus. Integral of g is integral of g plus minus integral of g minus. Right? Okay, so what do I want to do? So let us look at h equal to h plus minus h minus, which is f plus g, which is equal to f plus minus f minus plus g plus minus g minus, right? The trick is to bring all functions with positive sign to one side, all negative functions to the other side. That means I am going to rearranging term. Therefore, h plus f minus plus g minus equal to f plus g plus minus plus h minus. Do you understand this? I am rearranging the term. Forget this below. From this I am getting this. Now these are all non-negative measurable functions, right? And integral is additive on such functions, on non-negative functions. Therefore, integral of h plus f minus plus g minus equal to integral of f plus g plus h minus. Do you understand? Next, as I said, integral is additive. Therefore, this fellow equal to integral of h plus integral of f minus plus integral of g minus. And here also the same reason, integral of f plus integral of g plus integral of h minus. And now next thing is, since we proved f, g, h are all integrable, their positive and negative parts are also integrable. They are therefore their integrals are finite. Therefore all these fellows are finite. Right? Therefore I can bring this side, integral of h plus, bring this to this side, that is subtract integral of h minus, which is a finite quantity. Therefore I get integral of h minus. Right? And subtract integral of f minus from here, and here therefore you do that. Therefore I am going to get this equal to integral of f plus minus integral of f minus plus integral of g plus minus integral of g minus. Is that okay? But this is by definition integral of h. This is by definition integral of h, f, and this is definition integral of g. Therefore I have proved this result. So pause, review, proceed. So you see that? It's a very interesting proof, right? So h equal to h plus h minus, that is equal to f plus minus f minus, g plus minus g minus. Bring all those things to thing and apply the linearity of the integral or non-negative measurable function. That's the trick. And also on the way we observed each of the integral h plus, g plus, f plus and their minus versions, they are all finite. That's also very important. That's where we use the integrability. Is that okay? So what remains? Let me see whether I have time. Okay. What remains is now scalar multiple. Okay. Let us do that. So let us start with C, a scalar, and F integrable. Then I want to say CF is integrable. This is easy. Why? Because CF, okay, is in L plus if only this is integrable. But this is less than, this is equal to mod C into mod F, right? Therefore, integral of mod CF equal to integral of mod C into mod F. But remember, a positive homogeneity of the integral or non-negative measurable function, say this is mod C into integral of mod F. This is finite quantity. And this is a finite thing. Therefore, we have proved this is finite. Okay, therefore, mod CF is integrable. And hence CF is integrable. Okay, pause, review, proceed. So it's integrable. Next thing is I want to show you. So what do you want to show? We want to show integral of CF equal to integral of C times integral of F. This is what we want to show. So as usual, let us look at C, easy different case. When C is 0, notice that this is integral of 0. This is 0 times integral of F. And notice that this is a finite number, 0 times F 0. Integral of 0 is 0, that we already know. Why? We did not say if F is a measurable function, any simple function, less than or equal to F will also be 0. And for 0 the function, if we have seen that the integral of S will be 0. So this will be 0. Do you understand what I said? If F is 0, then integral of F is 0. Okay, I gave a proof. Okay, just to go through the proof. Okay, therefore this case is taken care. Therefore, second case is when C is positive. Right? When C is positive, let us look at this case. Okay, then I have to look at CF, integral of CF. That means I have to look at CF plus minus CF minus, what they are, right? But what is CF plus? Notice that C is positive, therefore CF plus is just a CF plus, and this is again CF minus. Is it okay? Therefore, integral of CF by definition is integral of CF plus minus integral of CF minus, but this is integral of CF plus minus integral of CF minus, right? Now, don't worry about this sign. Now, positive homogeneity will tell me this is integral of C into F plus, and for the same reason, C, positive thing will say this is C times integral of F minus, but this C is common, therefore integral of F plus minus integral of F minus, but that is integral of CF. Okay. So, when C is greater than 0, result is true. Pause, review, proceed. The next thing is C is less than 0. So let us look at the case C equal to minus 1. Therefore, CF is minus 1 times F is F minus F. But what is minus F of plus? Notice this is just F minus F minus. Yeah. The minus F plus will be F minus, and minus F minus will be F plus. Do you follow what it means? Because minus of F plus at X is maximum of, what are the two things? Maximum of minus Fx and 0. Right? So if Fx is positive, okay, then this will be negative. Therefore it has to be 0, which is negative. Yeah? Therefore it's minus of F. Okay? Are you following? So please check. Therefore, integral of minus F is going to be integral of minus F plus minus integral of minus F minus, but this integral of F minus of integral of F plus. But this is negative of integral of F plus minus integral of F minus. But that is integral of F. So I wanted to check this. I showed, if I try to explain, you will only get confused, get confused. What we are saying is minus of f, it's a plus is nothing other than f minus. And say, once you prove that, the other case is also similar. Okay, I used it. Now suppose c is negative. Then I can write c as minus c times minus 1. F, right? Therefore, this is minus c times minus f. Right? Remember, therefore, minus c is positive. Therefore, integral of minus c times minus f by definition is minus c times minus f. You understand this? Because this is positive homogeneity comes out. For c positive, we had already proved the result. Therefore, this comes out. But then just now we saw this is minus c. This is minus of integral f. But that means c of integral f. Okay. So that proves the result. So what you have shown is the set of integrable function is closed under addition and it's also closed under scalar multiplication. Therefore, it is a vector space. Right? Not only it's a vector space, we also proved something on the way. The map f going to integral of f is a linear map. That also we proved because integral of f plus g is integral of f plus integral g and integral of cf is c times integral of f. Therefore, the map is a linear map. Okay. So the theorem actually proved is not only algebra of integral function. We also said the integral is a linear map on the set of integrable function, on the vector space of integrable functions. Okay. I hope you enjoyed. Please go through. There are a lot of subtle points which I said which are usually not found in books, and I know it may be a little confusing, but just go through it. As I said, you don't have to understand 100%. This kind of understanding comes with more and more exposure. Okay, as you grow maturity and you go more exposed to measure theoretical arguments, Lebesgue measure theory and their theorems and proofs, you will become more confident. But it's good to see that kind of general intuitive ideas, what it means. Okay, please go through that. I hope you enjoyed. We'll meet again in the next session.